Alright guys, welcome to the channel. We're going to be solving the first question from the 7th chapter of the Hibbeler textbook Engineering Mechanics, and in this one we need to determine the shear force and moment at points C and D. So we have two different supports at point A and B. So we're going to start with the free body diagram of the whole system, and we're going to find the reactions at A and B, and after that we can do sections at C and D. And we can consider this section for finding the internal forces at point C, and for D we can pick the DE part of this beam for all the internal forces at point D. So let's start with the free body diagram of the whole beam. So at point E we have the 300 pounds, at point B we have 200 pounds. Also we have a pin support at the point B, which means we have both X and Y component. We can just consider one direction for now, maybe both positive X and Y components. We can call our X and Y in here. We have 500 pounds applying in here. And if we look at A, we have a roller, which means we only have a normal force or AY in here. So that's pretty much all the forces that we have. And we are in equilibrium. We're going to use our equilibrium equations. Let's start with sum of all forces equals 0. So if we do that for x, we can see that we only have bx in x direction, which means bx is 0. And we can go for fy, sum of all forces in y direction, but we already have two unknowns, which means we need to move on to our moment equation. We have the most unknowns at b. So we can do some of the moments about b equals 0 counterclockwise positive as always, although we know that bx is 0, so it doesn't matter going with point A or B. We can figure out one of the unknowns. So if we do at B, we have the moment of 300 pounds force about B, which is clockwise moment, so negative 300 times the distance from B to E, or this distance, which is 6 plus 2, 8. And we have the moment of 500. This one's counterclockwise, so positive plus 500 times what we have from here to here, which is 4 plus 4, another 8. And we have the moment of AY about B. This one's also clockwise, so negative minus AY, and the distance is from A to B, which is 4 plus 4 plus 6, or 14. So this will be equals 0. AY would be 500 times 8 minus 300 times 8 divided by 14. We know this will be 200 times 8. So 1600 divided by 14, which is going to be 114.29 pounds. So that's going to be our AY. Now if we do sum of all forces in Y, we can find BY as well. But we really don't need to find BY, because what we care about at this point is this part of the beam that I'm highlighting in yellow for finding the internal forces at C, and this part of the beam for finding the internal forces at. So we don't need to find the Fy, but if we want to do, we just have to do sum of all forces in Y equals 0. Let's move on to finding the internal forces and bending moment at point C. So this will be our point C. At A, we have our AY, which we found is 114.29 pounds. We're going to consider one shearing force and one axial force. Let's call this our axial force, and this V our shearing force, and this will be MC, or our bending moment. And we also have the 500 pounds applying at this point, and that's pretty much everything. So if we do sum of all forces in y direction equals 0 for this free body diagram, so we are talking about the new free body diagram that we have. So we're gonna have AY minus VC equals 0, minus 500 equals 0, minus 500 equals 0. We have three forces in y direction. AY is 114.29. So our VC would be 114.29 minus 500. We're going to get a negative sign that shows our assumption for VC is not correct. It's actually upward. So 114.29 minus 500 minus 385.71 pounds. So we found the shearing force. If we do sum of all forces in x equals 0, we can figure out that NC is 0, so no axial force for the point C. And now we have to find the MC. If we find the sum of all moments about point C, we have the bending moment that we are trying to figure out. We have the moment of 500, which is in this direction. So counterclockwise 500 times. We're looking for the distance from C to the 500, which is this distance, so times 4. And we have the moment of AY, which is clockwise. So this is going to be the moment of AY. So clockwise negative minus 114.29 times the distance from A to C, which is 4 plus 6, or 10. So now our MC, or the bending moment, would be 114 times 29.29 times 10 minus 2000. So it's going to be minus 857.1 pound-foot. And the negative sign shows that the assumption was not correct and the moment is actually clockwise. That's pretty much everything for internal forces at point C. Now we are going to the third free body diagram of the DE part of the beam to find the internal forces. So if we look at that part of the beam, we have the 300 pounds force and all the internal forces and bending moment. So we can call the axial force ND, we can call the shearing force VD, and let's just consider a bending moment of MD. And now we have to figure these three unknowns. We are in equilibrium. We're going to use our equilibrium equation. Let's start with our Fx. The only force is ND, so that shows that ND is 0. We're going to do sum of all forces in y equals 0. We have VD minus 300 pounds equals 0. That shows our VD is 300 pounds. So we found the shearing force. And we're just going to have to do the moment about the counterclockwise positive as always. And we have MD, since we assume that the MD is counterclockwise. So we have a positive MD minus 300 times the distance from D to end of the beam, or D to E, which is 2 feet equals 0. And that shows that our MD is 600 pound-foot. We did not get any negative sign. That shows our assumption was correct. And the moment is counterclockwise at point D. So yeah, hope everything was clear. That's pretty much everything for this one. Let me know if you guys have any questions. We are covering 3 different textbooks for engineering mechanics in this channel. Feel free to check out the playlist and let me know if you guys have any specific problem that you want me to cover in the next videos. And you guys take care. I'll see you in the next one.